So in this video we examine MR, the mole, and we begin to look at reacting mass calculations. This is a fundamental part of the amount of substance topic, and it's absolutely vital that you understand this area if you're to progress through your A-level. So there is one thing that we have to clear up right at the beginning. So you quite often see these terms used interchangeably, and I just want to make sure that when people use them, they're really typically talking about the same thing. So there's relative formula mass and there's molecular mass. Strictly speaking, a lot of people use MR when perhaps they shouldn't, because if it's called molecular mass, then it should really be about molecules. But you might find that that distinction isn't really held to in a lot of questions and textbooks. So regardless of which one we're using, relative formula mass or molecular mass, what we're referring to is the total mass of all the relative atomic masses of the elements in a formula. So you're going to be relying quite a lot on your periodic table. Now at GCSE, all of the atomic mass numbers, all of the relative atomic masses were whole numbers, they were integers, except for chlorine and copper. So on the GCSE periodic table, there was only chlorine and copper that had a decimal place in their atomic masses. That's because they really wanted to just use those as examples when it came to isotope questions. But at A-level, every atomic mass value on your periodic table is to one decimal place. So there's that level of precision when you're looking at MRs too. Now for the rest of the video, we're going to be using, or at least I'm going to be using, the A-level periodic table. So when I give any examples, I will be using the relative atomic masses that are given on AQA's A-level periodic table. So just to sort of illustrate what we just simply mean from this title here about the total mass of all the relative atomic masses of the elements in a formula, I'm just going to give a very simple formula. We're going to do a couple of examples anyway, just to start us off, just to make sure that we understand what I'm saying here. So I'm going to list a few formulae, and then we're going to do the MRs for those formulae. So I've gone with carbon dioxide, magnesium oxide, and potassium chloride. Okay, so we're starting with carbon dioxide, and carbon has a relative atomic mass of 12.0, and there's only one of those. And then we have two oxygens, each of which are 16.0. So just doing this like the longhand, but just to make it clear. So that gives us a total of 44. Okay. Magnesium oxide, we've got 1 mg and 1 O. So the relative atomic mass of magnesium is 24.3. So at your GCSE, it would have just read 24. Oxygen is 16.0. So that gives us a total of 40.3. And then finally, we've got potassium, which is 39.1. Again, at GCSE, it would have just been 39, plus chlorine, which is 35.5. And that gives us a total of 74.6. So before we go any further with MR, we have to make sure that we understand what this concept, the mole, is. So the mole is a measure of an amount of substance, and it refers to the mass of a specific number of particles. So if we say we have a mole of something, then we know exactly how many particles of something that we have. It's no different than saying a pair of socks, or a dozen eggs, or a ream of paper. So a pair of socks is 2 socks, a dozen eggs is 12 eggs, and a ream of paper is 500 sheets of paper. Now this specific number is known as Avogadro's number, and that has a value of 6.022 times 10 to the 23. So it is an enormous number. I mean, it's just phenomenally large. If you were to count, every second up to 6.022 times 10 to the 23, then you would need approximately 1 million histories of the universe. So that's how large that number is. So the history of the universe is in the order of 10 to the 17 seconds. And here we're talking about a number that is 10 to the 23. So Avogadro's number is fundamental to the concept of the mole. And so if we say that we have a mole of a substance, then we're saying that we have this 6.022 times 10 to the 23 units of that substance's formula. So I'm going to expand a little bit on what we've just seen on the previous slide. But just before we do that, there's something else to just establish first. And this is that the mass of 1 mole of any substance is the MR of that substance in grams. So earlier we said that the MR of carbon dioxide, for example, was 44. And if we want to know what the mass of 1 mole of carbon dioxide is, it's going to be 44 grams. So I'm just going to write out a few examples that bring together the things that we've said so far in this video. So I've chosen 4 substances. I've chosen iron, chlorine, sodium oxide and calcium carbonate. And then I've looked at the relative atomic masses of the elements in those formulae. So iron is just Fe, so it's 55.8 on the A-level periodic table. So that means its RFM or MR is 55.8. And we know that the mass of 1 mole of iron is going to be the MR with grams after it. So it's going to be 55.8 grams. What that also means is that if we have 55.8 grams, then we know that we have 6.022 times 10 to the 23 lots of Fe atoms. If we look at chlorine, so chlorine's formula is Cl2, so there are 2 chlorine atoms. So we're going to have 2 times the relative atomic mass of chlorine, which is 35.5. So that means that the MR here is 71.0. That means the mass of 1 mole of chlorine is 71.0 grams. And then that means we have 6.022 times 10 to the 23 lots of chlorine molecules. And then we've got, similarly, we've got sodium oxide. And because we've become experts at determining formulae, we know that the formula of sodium oxide is going to be Na2O, because that we know that Na sodium is a group 1 metal. We know that oxygen is in group 6. We know that this is an ionic compound, because the useful rule of thumb is that a metal and non-metal form ionic compounds. So the sodium is going to be a +1 charge ion, and the oxide ion is going to be 2 minus. So we need 2 sodium ions for every 1 oxide ion, which is why we have the formula Na2O. So we have 2 sodiums. They have a relative atomic mass of 23.0. Oxygen has a relative atomic mass of 16.0. So that means the relative formula mass of sodium oxide is 62.0. And if we have 62.0 grams of sodium oxide, then we have 1 mole of it. And then obviously that means that we also have, we know if we have 62.0 grams, then we have 6.022 times 10 to the 23 lots of sodium oxide, lots of Na2O. And then finally, exactly the same thing with calcium carbonate. We end up with an MR of 100.1. We know therefore that 1 mole has a mass of 100.1 grams, and we know that if we've got 100.1 grams of calcium carbonate, then we have 6.022 times 10 to the 23 Avogadro's number lots of calcium carbonate. Now let's just take that a little bit further, and let's just focus on sodium oxide. So if we have 62.0 grams of sodium oxide, then we have 6.022 times 10 to the 23 lots of sodium oxide. So I can write what I've just said like I have done here in the blue. Now we've got 6.022 times 10 to the 23 lots of sodium oxide, but let's think about what sodium oxide is, okay? What is that made up of? Well, we said that that formula was 2 times the sodium ions and 1 times the oxide ions. So that means we can we can extend our knowledge and say that our 62.0 grams of sodium oxide means that we have twice that number of sodium ions, so 2 times 6.022 times 10 to the 23, and also 6.022 times 10 to the 23 oxide ions. So we have Avogadro's number of sodium oxide, but that sodium oxide is made up of sodium ions and oxide ions, and we can be now a little bit more specific about how many sodium ions is in a mole of sodium oxide and how many oxide ions are in a mole of sodium oxide. Sometimes you have to work out what the mass of 1 atom, ion or molecule is. So we're going to look at two examples here. So we're going to ask ourselves the question, well, let's start with what we definitely know. So we definitely know that 1 mole of magnesium atoms has a mass of 24.3 grams. And we now know what we mean when we say 1 mole of magnesium atoms. And that is that if we have 1 mole of magnesium atoms, we have 6.022 times 10 to the 23, so that's Avogadro's number, atoms of magnesium, and they equal 24.3 grams. So if we want to know what the mass of 1 atom of magnesium is, we have to divide both sides by Avogadro's number. So therefore we've got 24.3 divided by Avogadro's number, and that equals 4.04 times 10 to the minus 23 grams. So perhaps unsurprisingly, the mass of an atom is incredibly small. Let's just look at another example. So we're asking ourselves the question, what is the mass of 1 molecule of hydrogen? So it ends in gen. That's a sort of a way of remembering which the diatomic molecules are. So we know that 1 mole of hydrogen, and we know that hydrogen has the formula H2 molecules, and we add up the relative atomic masses, and hydrogen is very easy. Hydrogen atom has a relative atomic mass of 1.0, so we add two of them together, so we have a molar mass of 2 grams, or 2.0 grams. So that means we have 6.022 times 10 to the 23 molecules of hydrogen, and they have a mass of 2.0 grams. Therefore, if we want to know what the mass of 1 molecule of hydrogen is, we've got to divide both sides by Avogadro's number. So 1 molecule of hydrogen is going to have the mass of the molar mass divided by Avogadro's number, which equals 3.32 times 10 to the minus 24 grams. Again, a molecule of hydrogen has an incredibly small mass. So I'm sure you've seen this triangle before. It's a way of bringing together mass, MR, and number of moles. So we can use that triangle. So mass is going to be number of moles times MR. So I tell you what, I'll just add in here. So we're going to put a times there, and then what we've got here is divide, and you know hopefully how to use these triangles. If you want to know the MR, you would put your finger or thumb over MR, and you would know then that was mass divided by moles. If you want to know number of moles, it would be mass divided by MR, and so on. So whether you actually learn it as a triangle, I have to admit I never learnt it as a triangle at school, but you do need to know how to work out number of moles from mass and MR. You need to know how to work out mass from number of moles in MR, and you need to know how to work out MR, etc. Okay, so we're going to start applying shortly our knowledge of moles and MR to work out calculations, or to do calculations involving reacting masses. But before we do that, we just need to make sure we're on top of this term stoichiometry. Now, it's a really strange word. You may or may not have heard it before, but it's quite likely you'll come across it. I'm deliberately using it because it's not something to be frightened of. It's really, what it really refers to is making sure that our equation is balanced. So it's based on the conservation of mass, and it's all to do with the ratios of reactants and products that we have in a reaction. So here we have got a balanced equation of N2 plus 3H2 goes to 2NH3. So nitrogen and hydrogen are reacting to make ammonia. Now, one of the things that I personally always do whenever I'm using a reaction equation, and particularly in calculations, is that I make sure that I write the ratios above the equation. So really all I've done is I've put the numbers in front of the formulae above them and sort of spelt out the fact that they're ratios. Now you may think, what's the point? I'm just repeating information that the equation's already given me, but it helps remind me when I'm doing calculations to take into account those ratios. And it also is emphasizing the point that they are ratios. So if we just explore that a little bit further, what this equation is telling us is that if we had one molecule of nitrogen, we would need 3 molecules of hydrogen, and we would make 2 molecules of ammonia. Okay, fine, yeah, I mean, sort of obvious. But because this is ratios, what if I had 10 molecules of nitrogen? Well, then I would need, it's a ratio of 1 to 3, I would need 30 molecules of hydrogen, and I would make 20 molecules of ammonia. Okay, that's fine, yeah, I'm sure your again's going, yeah, I'm nodding, it's all fairly straightforward. Well, okay, and I could, ramp it up a bit. I could say 1 mole. If I had 1 mole of nitrogen, well, I would need 3 moles of hydrogen, and I would make 2 moles of ammonia. And what if it was, I don't know, 0.05 moles of nitrogen? Well, then I would need 0.15 moles. I would need 3 times as much. Remember, the ratio is 1 to 3. And I would make 0.1 moles, and so on, right? And this is why it's important. It becomes important because when we're doing chemistry calculations, we're not worried about 1 molecule, and we're probably not going to be fortunate enough to have it in things like 1 mole. But where we are going to be worried or interested or need to have a grasp is when we're looking at small or unusual or not so obvious values, and thinking about how we use those numbers to work out how much of something else we either need or we're going to make. Okay, so now we're going to start applying everything that we've learned in this video up to this point to reacting mass calculations. So they're going to start off fairly straightforward, and they're going to get progressively harder, and then certainly the last couple, or the last 2, are probably going to be, well, at first glance they may appear to be a challenge, but fingers crossed by that point you will be in the flow and you won't find them as difficult as you might have done. So just before we look at the first question, I just want to say something about significant figures, and this applies to any calculation in your in your GCSE or A level, but particularly your A level. And the general rule, so it's a rule of thumb, is that you shouldn't quote a final answer to more significant figures than whatever the least accurate number you were working with, or perhaps it's not least accurate, maybe it's least precise, really, actually. So if the numbers you were using were all 3 significant figures, then your final answer should be to 3 significant figures. If the numbers you were using were a mixture, say one was 2 significant figures and the rest were 3, then your answer would need to be to 2 significant figures. So the final thing to say about this is, of course, we're talking now about your final answer. What you shouldn't do is round during your calculation process, because if you do that, you'll end up with an answer that is quite a way away from the correct answer. So in any multi-step calculation, just keep the number in your calculator, and only at the very end do you round and do you write your answer to the correct number of significant figures. Okay, so we got this question, what mass of hydrogen is produced when 192 grams of magnesium is reacted with hydrochloric acid? So first thing to notice is they've given us this equation in words, really. In fact, they haven't even given us the word equation. So we need to know more than the word equation. We need to know the symbol equation. So before we do any calculating, we have got to write a balanced equation. And so this goes back to the very first video in the amount of substance section, all about formulae. If you're not secure in your formulae, if you're not able to work them out, then you have got a fundamental problem at A-level chemistry. You could be really secure in the maths regarding this question, but without a correctly balanced equation without you determining that on just writing it and coming up with it, then you can't really proceed with answering the question. Okay, so we know that magnesium is reacting with hydrochloric acid, and what we should remember is if we're reacting a metal with an acid, we make a salt and hydrogen. So our salt is going to be magnesium chloride. So we need to be confident that we can write the formula of magnesium chloride. And we're also going to make hydrogen. So we need to remember that hydrogen is diatomic. And we need to now to make sure that our equation is balanced. So before you ever balance an equation, you've got to make sure that your formulae are absolutely correct. Because if you get the formulae wrong, it doesn't matter what you do with the balancing. It's not going to be the correct equation at the end. We're going to need 2 hydrochloric acids, and that's now correctly balanced. All right. Now, just to give you a sort of a process, I'm going to write an order of words down on the side, and I'll explain those once I've done that. So I've written mass, MR, moles, MR, mass, because this is going to be the order. This is going to be the order that we're going to use the information in to solve or to get the answer to this question. So we are given the mass of magnesium. It's 192 grams. And then just before we proceed, what I'm going to do is I'm above the equation. I'm going to write the ratios, like I said. I always did whenever I do a calculation like this. So it's only now really that we're ready to go. All right, so the MR of magnesium. So remember, MR is the relative formula mass. It is the formula, okay? So the formula of magnesium is simply Mg, so no problems there. So we have an MR of 24.3. I got that from the periodic table. Now, if we think back to the relationship between mass and MR, we can work out moles. So mass divided by MR is the number of moles. So that would give us a value of 7.90. And what I'm doing is I'm leaving, it's actually a much longer number than that, but I'm leaving it in my calculator. So we know that what we've got in our reaction is 7.90 moles of magnesium. And thinking back to our stoichiometry and our ratios, the ratio between magnesium and hydrogen in this reaction is a ratio of 1 to 1. Okay, so that means that if we are reacting 7.9 moles of magnesium, and they all react, so we're not considering limiting reactants or anything like that here, then we are going to make, we've got a 1-to-1 ratio with hydrogen, so we're going to make 7.90 moles of hydrogen. So I've still got the number in my calculator. And the MR of H2 is 2. Okay, and we know that moles times MR equals mass. Okay, so 7.9 times 2.0, okay, comes up with an answer of 15.8. Okay, so we've got 15.8. And actually, the next digit is 0, and we started with 192 grams of magnesium, so that was 3 significant figures. So actually, this is correct, the right number of significant figures. So if we had 192 grams of magnesium and this reaction took place, then we would make 15.8 grams of hydrogen. Okay, so this question is what mass of aluminium oxide is produced when 135 grams of aluminium is burned in oxygen. So the first thing that we need to do is we need to write a balanced equation. So actually, why don't you pause the video for a second and have a go at writing that, and then I'll write the correct answer and you can compare your answer with mine. So hopefully that's what you got. Of course, you needed to know the formulae before you could balance it. So aluminium is just a metal, so it'd just be Al. You needed to remember that oxygen was a diatomic molecule as an element, and you needed to be able to work out the formula of aluminium oxide using the charges that the ions would have. So I'm going to do my ratios. So it's 4 to 3 to 2. Okay, and then I'm just going to write down the side as I did before, the mass, mR, moles, etc. Okay, and I know that mass divided by mR equals moles, and I know that moles times mR equals mass. All right, so ready to start. So I was told I had 135 grams of aluminium, and the mR of aluminium is 27.0. So that means I can work out the number of moles. So that's a nice round number of 5. And then I'm trying to work out how much aluminium oxide is made. And the ratio of aluminium to aluminium oxide is 4 to 2 or 2 to 1. So that means if I have 5 moles of aluminium, I'm going to make 2.5 moles of aluminium oxide. I can then work out what the mR of aluminium oxide is, and that's 102. And then I know that moles times mR equals mass, and that's 255 grams. The most common mistake that people make is with the mR. So the most common mistake is they see 4Al, and then so they do an mR of 4 times 27. But that's what I'm trying to stress earlier. The mR, or the RFM, is the total of all the relative atomic masses of the elements in the formula. So those big numbers in front, those ratio numbers, the 4s, the 3s, the 2s, they do not matter when it comes to mR, because we take account of those 4s and the 3s and the 2s in this equation when we look at the ratios, when we go from the moles of one to the moles of another. So my 4 to 2 took into account that 4 in front of aluminium and the 2 in front of aluminium oxide. The mR is simply the formula. Okay, so here we are reacting potassium with water. So this was a classic reaction in your GCSE. If you remember, potassium is an alkali metal, and so it reacts with water, it reacts violently, and you would get an alkali, you get potassium hydroxide and hydrogen as the products. So have a go at writing the equation, and I'll write it up in a second. Okay, so we're basically ready to go. Now, just got to pay attention for little things that might catch us out. So notice that the mass we're given, 195 milligrams of potassium, so it's milligrams. Now, when we're talking about moles, our unit is grams. So the first thing that we need to do is we need to convert that 195 milligrams into grams. Now, milli means a thousandth, so we've got 195 thousandths of a gram. So our mass of potassium is 0.195. Okay, and our mR of potassium is 39.1. And so our number of moles equals 0.195 divided by 39.1, which equals 4.99 times 10 to the minus 3. Now that number I've written is rounded slightly, but I've kept the original number in my calculator. Now the ratio of potassium to hydrogen is 2 to 1, which means I have half as many moles of hydrogen. So I'm going to divide the number in my calculator by 2, and that gives me 2.49 times 10 to the minus 3 moles. And I know that the mR of hydrogen is 2.0, and so I multiply these together to get the mass. And to 3 significant figures, it is 4.99 times 10 to the minus 3 grams. Okay, so here we have a classic reaction, one with a practical use. So as you can see, railway lines are welded together using this reaction. So this is a reaction between aluminium and iron 3 oxide. And we get iron as a product, molten iron, molten because it's such an exothermic reaction. And that means we also get as our other product, it must be aluminium oxide. So again, that's the first thing we have to do, is we have to write a balanced equation. So pause the video and have a go at that, please. So there's our equation. And just before we start, just pay attention to the fact that they've given us the mass in kilograms. So obviously we have to work in grams when we're doing chemistry, so we need to convert that into grams. Well, there are 1,000 grams in a kilogram, so that's fairly straightforward. So we are starting off with 1,000 grams of iron 3 oxide. So our MR of iron 3 oxide is 105.8. And so the number of moles is 1,000 divided by 105.8, which equals 9.45. Okay. And our ratio of iron 3 oxide to iron is 1 to 2. So that means we have twice as many moles of iron as we do iron 3 oxide. So that means the number of moles of iron that we are going to make is 18.9 moles, and we know the MR of iron is 55.8. So therefore the mass of iron that we're going to produce is 18.9 times 55.8, which equals 1,054.8 grams. And of course we need to do this to the right number of significant figures, which is 3. So actually our final answer is going to be 1,050 grams to 3 significant figures. So this is a reaction that will feature in 2 places actually in the A-level. I mean, it'll only feature very briefly, but when we do alkanes, we have to look at removing the pollutants when alkanes are burnt, although it's not specifically the alkane that's the problem, it's the other substances that are present in the fuel. But also, because this involves calcium carbonate, will also feature very briefly in group 2, because calcium is a group 2 element. Now we need to write the balanced equation. I'm going to ask you to do that in a second. But just notice that if you read the text, it says sulfur dioxide is removed from the air by reacting calcium carbonate in the presence of oxygen. So actually our reactants are going to be calcium carbonate, sulfur dioxide and oxygen. So when you write your balanced equation, please bear that in mind. And this is a neutralization reaction actually. Calcium carbonate is a base, sulfur dioxide is acidic. So actually, just as a sort of side point, any metal oxide is a base and any non-metal oxide is acidic. If we dissolved sulfur dioxide in water, we would eventually arrive at sulfuric acid. So our products here, I'm just going to tell you what the products are because I feel that's only fair. Our products are going to be calcium sulphate and carbon dioxide. So calcium carbonate is reacting with sulfur dioxide and oxygen to produce calcium sulphate and carbon dioxide. So if you could pause the video and try and write a balanced equation for that, please. Okay, so hopefully that's what you got. Have to pay attention to the information again. This time they give it to us, they give the mass to us in tonnes. So 1 tonne is 1,000 kilograms, and we know that a kilogram is 1,000 grams. So we are actually starting with 1 million grams of sulfur dioxide. So I'm going to write that in standard form because just to make life a little easier. Notice the precision. It's 1.00 tons, so I'm going to have 1.00 times 10 to the 6 grams, that's grams, okay, of sulfur dioxide. And then the MR of sulfur dioxide is 64.1, which means that the number of moles is 1.56 times 10 to the 4. Okay, and then very straightforward actual equation. In fact, this time we're trying to work out how much calcium carbonate there is, but it's still a 1-to-1 ratio, so that means our number of moles is the same. So that's 1.56 times 10 to the 4. And calcium carbonate, that was actually one of the ones that we did right at the beginning, and the MR of that is 100.1, sorry. And so that means the mass of calcium carbonate needed is 1.56 times 10 to the 6 grams, or 1.56 tons. Right, so this is a different type of question. This is one that might throw you when you first read it, but actually, if we take our time to think about it, isn't actually as difficult as it might look. So we're told we've got 5 grams of hydrated sodium sulphate crystals, and then they give us a formula, but they have this letter N. So this dot, NH2O, it's a water of crystallization, so it means that we have N water molecules for every unit of sodium sulphate that there is. And then we heat it, and after we heat it, we get 2.20 grams of anhydrous sodium sulphate. So we'll look at what that means in a second. And the constant mass is important, because what that's telling us is if the mass remains constant, then that means the reaction is finished. It's not always obvious. I'll come back to it when we see the equation, but it's not always obvious that we know a reaction such as this is finished. So, and then we have to work out the relative formula mass, or the relative molecular mass, sorry, of the hydrated sodium sulphate, and we have to work out the value of N. So, the fact it says hydrated at the beginning is because of the water that's present, okay? And then when they tell us anhydrous, what that means is that all of the water, all of that H2O is being removed. So an at the beginning of a word normally means without. And that's why if you think of anesthetic, it's aesthetic with an, and an aesthetic means feeling, so anesthetic means without feeling. So now let's start looking at the equation itself. So we're starting with sodium sulphate, or hydrated sodium sulphate. Okay, so there's the formula, and we're simply heating that, and what we're making is anhydrous sodium sulphate, so that's the sodium sulphate without the water, so that must be Na2SO4, and then obviously our equation has to be balanced, so we must have NH2O. And then thinking about the ratios above, well, there's one of the hydrated sodium sulphate, sorry, and there's one of the anhydrous, and then, well, we don't know what N is, but the ratio must be 1 to N for that at the end there. So I'm going to write the mass MR moles that I normally have down the side, but I'm just going to write the first 3 terms. We were told that we had 5.00 grams of the hydrated and 2.20 grams of the anhydrous sodium sulphate. And now we've got 1 term on the left and 2 on the right. This is a decomposition reaction, and it's thermal decomposition. So decomposition means it's breaking down into a simpler substance, and thermal means through the action of heat. So we can use the conservation of mass here. So the total mass of the right-hand side must equal the total mass of the left-hand side. The left-hand side is 5 grams. The right-hand side is 2.20 grams plus whatever the water is. Well, the water must be 2.80 grams. Okay, so normally next we look at MR, and we divide our masses by MR. Now we've got 3 masses, but actually we don't know the correct or true formula for the hydrated sodium sulphate, so there's nothing we can do there. But we do know the true formula of sodium sulphate, and we do know the true formula of water. So we can work out the number of moles of sodium sulphate, the anhydrous sodium sulphate, and we can work out the number of moles of water. So the MRs of those 2 substances are 142.1 and obviously 18. So we can work out the respective number of moles of each. So we divide their masses by their MRs, and that gives us 0.0155 and 0.156. And so these are also now ratios. So our ratio of sodium sulphate, anhydrous sodium sulphate, to water is 0.0155 to 0.156. So we need these to be whole numbers or integers, so we're going to divide through by the smallest number, and the smallest number is 0.0155. So if we divide that by itself, we get 1. And if we divide the 0.156, which was a rounded number incidentally, we get something very close to 10. So that means for every sodium sulphate we have 10 water molecules, so that tells us that N equals 10. So the true formula for the hydrated sodium sulphate is Na2SO4 dot and then 10H2O. So now we have the formula, we can work out the MR of hydrated sodium sulphate. So why don't you just pause the video, have a go at doing that, and we'll just check that your answer is the same as mine. Well, there was a quick way of doing it. We knew that the MR of sodium sulphate was 142.1. We know that the MR of water is 18. Well, 18.0, I should put that there. And there are 10 waters, so that's 180. So we just add 142.1 and 180 together, and that gives us an MR of 322.1. So that's the end of our looking at MR moles and reacting mass calculations. If you have any queries, you know where I am, so get in touch. And yeah, we'll be doing limiting reactants next.